Now in this chapter, we're going to look at rates from a completely different perspective. We're moving away from finance, and it'll probably be no surprise to you, we're moving into looking at rate as a derivative. There's hardly a chapter where calculus isn't dealt with in some way. So while previously the rates were expressed as a percentage, and we looked at the significance of the rates in APs or GPs really. Now we're staying with a rate. However, our interpretation of the rate now is how something is changing compared to something else. Now, when we start talking about changes in variables compared to another change in another variable, you're probably making the connection to gradient, and obviously connecting to gradient because gradient measures the rate of change of one variable compared to the other. And you also make the connection to finding the first derivative because that gives an expression for the gradient. So we see that the first derivative is also an expression for the rate of change in a quantity with respect to some other aspect of the quantity. A very good example of a rate of change is if we look at how distance changes with respect to time, distance and time, how they're changing, well, we know that measure, and that's called speed. So speed, we could say, is what you get when you differentiate distance with respect to time. So if you've got an expression for the distance travelled in terms of time, some function in t, then I think I won't complicate it with that. So if you've got the distance is, say, the time squared plus t, then if we take the derivative of that with respect to time, we get 2t plus 1, the change in the distance with respect to time is the equivalent of the speed, could be written or calculated as 2t plus 1. If we want the actual value of the speed, if we want to evaluate it, the actual speed or the first derivative, it's just like when you've wanted to evaluate the gradient. You want to know the actual number for the gradient, you have to know at what instant it is you're considering it. And so likewise here you'd have to know what the time was because the speed varies according to the time. Another example, if you wanted the rate at which the volume was changing over time, volume, then we would have dV dt. One small complication there is that volume is rarely given in terms of time. Volume is often given, if I thought about the volume of a box, of a cube, the volume is given with respect to the sides, because the volume is side cubed. We could find dV ds, no trouble, the rate and change of the volume with respect to the side. But, it becomes a little more complicated to find the rate of change of the volume with respect to time. No, it's not if you're given volume in terms of time, 2t squared plus 5, then dV dt, then expression for the rate at which the volume is changing with respect to time is 4t. And it just says here to evaluate, just like I was talking about over here, at any instant we want to know the rate of change, then we'll have to substitute a value in for our variable for time, sub that in, and we can evaluate the rate of change. Okay, let's have a look at these examples. So this is talking about a cockroach plague hit East Maitland last summer, but it was gradually brought under control. The council estimated that the cockroach population, P, in millions, T months after the 1st of January was given by this expression. No idea where they got that from, but looking at it, that's not so unfamiliar. We've got P in terms of T. If that was Y in terms of X, and I'm going to write it as minus X squared plus 6X plus 7, then I know that that graphs to give an upside down parabola. Now, going back and putting my P on it, so this would be P on the graph. This is time. So we can see that the population of cockroaches increasing, and then at some stage it starts to decrease. So this is going to be a critical point, I imagine. When did the population of cockroaches start to decrease? What do we know about the gradient at that point? Well, we know the gradient's going to be naught because it's an upside down parabola and the tangent is horizontal at that point. So there's lots of things that we know about this just because of the previous algebra that you have studied. And you know what? Really, there isn't anything new in terms of maths in this exercise. Yes, you will be differentiating and you'll have to have an understanding that the derivative is a rate, but that's about it. Okay, let's have a look at the question. Find an expression for the rate of change in the cockroach population. The rate of change, there's your keywords, rate of change. You have to become, really confident with making the connection between those words and the first derivative. So we want dp dt, the rate of change of the population with respect to time. Now, if you do this, if you say these things to yourself as you write them, it reinforces it for you. Think it to yourself. I'm getting the rate of change of the population with respect to time. And you can see that is 6 minus 2t. So the rate of change is just a nice straight line. It says, find the cockroach population. Oh, so back to the cockroach population. So we're not talking rate of change here. On the 1st of January, so this whole thing started 1st of January, so it must have been at the beginning, and the rate at which it was increasing at that time. So we've got to find two things. A hint, at the 1st of January, in this case, time is 0. So we want the population, and the population is 7 million. And just subbing t equal to 0. We found the rate at which it was increasing, and we've got an expression that says dp dt is equal to 6 minus 2t, and we've got t is equal to 0. The rate at which it is increasing, or the rate at which it is changing, is subbing t equal to 0 gives me 6 million. So the rate at which it is changing is, it's increasing at this stage. It's a positive number. The rate is a positive number. It's increasing at 6 million, and the unit of time is months per month. So that's pretty serious, isn't it? Yeah, we've got a plague of cockroaches. So no wonder they needed to bring it under control. It says, when did the council manage to stop the cockroach population increasing any further? And this is where, if you've been able to draw the graph, you can connect your understanding of these words back to the diagram. When did the population cease to increase any further? And clearly it's at this point here. at this t value. What's going on at that t value? We know that dp dt is equal to naught. What was our expression for dp dt? This 6 minus 2t has to be naught. 2t, take it to the other side, make it a positive, is equal to 6. T is equal to 3. 3 months later, the population ceased to increase. The graph of the population started to come down. When were the cockroaches finally eliminated? Well, what does that mean? If they're finally eliminated, how many cockroaches are there? I think P's got to be 0. And we've got to find when P was 0. So what do we know about P? It is minus t squared plus 6t plus 7 is equal to naught. Putting our quadratic equal to naught, I've factorised the quadratic. That then gives a solution of t is equal to minus 1. Well, minus 1, that's no real solution. We never talk about a negative time. And the other solution is that t is equal to 7, so it's after 7 months. So if you think about what the sorts of maths we did throughout those 4 parts of that question, not all of it was about the derivative. Certainly this last part, D, is not about the derivative. So, for many of these questions, it's more a test of your understanding what you're reading and relating that mathematically. Not every part of the question will you be doing the derivative. Not every part of the question will you be subbing into the derivative. You've got to really think about what the derivative is, how it relates in real situations, how is it interpreted, and what does an original function tell you in real terms. So you really need to read the question very carefully and get it really well sorted as to what the concepts are in the real situation that the question's talking about.